everyone, good afternoon. Welcome to this talk. The talk will be given by Francesco Dagnino, who is a PhD student here, and he's working on theoretical computer science and programming languages, and he will talk about how to generalize inference systems for more flexible definitions of both inductive and coinductive stuff.
Okay. So thanks, Luca, for the introduction. Thank you for coming. So today I will talk about recursive definitions, and in particular about their semantics, their possible semantics. And everything will be formalized in the general framework of inference systems in order to have a mathematically rigorous treatment. So, brief outline. So we start by introducing the framework of inference system, discussing their possible semantics, interpretations, which are the inductive and the coinductive one, and highlighting the limitation on the standard theory. Then I will move to a smooth extension of this theory we proposed last year, which is based on the notion of coaxioms and allows more flexible definitions. And finally, I will briefly sketch an application to model the semantics of non-terminating programs. So, starting from the very beginning, what is a definition? A definition can be represented in this way. We have an object we are defining, a connective, and the body of the definition. And this is said to be recursive if in the body we have a reference to the object we are defining. So, for instance, if we want to define the predicate is ancestor of, we will say that A is an ancestor of B if either A is a parent of B, or we can find an X which is a parent of B and such that A is an ancestor of X. So this definition is clearly recursive, since in the last line of the body we have a reference to the object, to the predicate is ancestor of. And if you think a minute about this definition, it could be clear that this matches the intended semantics, but not all the recursive definitions are so easy to understand. And so we need a much more formal representation. In this talk, we will use a rule-based formalism. So this definition can be translated in this way. So rules are connected by a disjunction. Each rule should be read to the top, from the top to the bottom as an implication, and all the elements above the line of a rule should be read as a conjunction. So this definition sounds something like if A is a parent of B, then A is an ancestor of B, or if X is a parent of B and A is an ancestor of X, then A is an ancestor of B, and this is exactly the same definition written above. So more formally, what are the ingredients of this framework? So we have a universe of judgments, which is a set. Simply, this represents the domain of our discussion. Then we have an inference system, which is a set of rules. Each rule is a pair, PR over C, where PR is a set of judgment called premises, and C is a judgment, which is the conclusion of the rule. And the intuitive meaning of each rule is that if the premises holds, then the conclusion should hold as well. So it's again an implication. There are special rules with where the set of premises is empty. These are called axioms, and intuitively represent judgment that always holds without any precondition. And that's all. So with these things we can write down our definitions, but so we need now a semantics, so a way to interpret the definition. This is like syntax. We need something to interpret the definitions. So what is the semantics? Here is a set of judgment called the derivable judgment, and essentially this set contains all judgments that should be considered true in some sense. Okay. There are several approaches to define this set. In this talk, I will use a proof-theoretic approach. So I will say that the judgment is derivable if we can construct an object associated with this judgment that is like a witness or a proof of the validity of the judgment. These objects are called proof trees and are defined that way. It is not a very precise definition. We can give one much more precise, but for this talk it is enough. So a proof tree is a tree where nodes are labeled by judgments, and each node C with a set of children which is PR is associated with the rule PR over C in the inference system. So essentially, a proof tree is a tree where each branching point in the tree is justified by a rule, and it represents a very high-level structure of the reasoning we have to do, guided by the rules, to derive that a certain judgment hold. Note that leaves in the tree corresponds to axioms, since leaves has no children and axiom has no premises. So leaves represent in some sense the initial assumption of the reasoning, and we can follow the rules. Okay, an example, the same inference system as above. We had before we add some axioms to represent some parent relationship between some individuals, and we want to prove that judgment. So since the two individuals are not related directly by the parent relationship, we have to apply the second rule. So we apply that rule, and we have still something to prove. Again, we apply the second rule, and we have still something to prove, but the two guys now are related directly by the parent relationship, and so we can conclude the proof. And this is the proof tree for the judgment that says that Mary is an ancestor of John. And as you can see, all the leaves are axioms inside the parent relationship. Okay. So let's consider a running example to discuss the inductive and the coinductive interpretation, much more for computer scientists, perhaps. We consider lists of integers, and we consider both finite and infinite lists. So we have a finite list, which is a list in which you can reach the empty list in a finite number of steps, and we have infinite lists in which we can never reach the empty list. So we can continuously unfold elements from an infinite list, and we want to define the maximum of a finite or infinite list of integers. And the definition is that one. It's quite intuitive, I think. This says that the maximum of a singleton list is the unique element of the list. This seems quite reasonable. And if the maximum of L is an element Y, then the maximum of X followed by L is the greatest between X and Y. So if you think a minute about this, it is quite natural as a definition. So it simply says that to compute the maximum of a singleton list, we have nothing to do. And to compute the maximum of a compound list, we first compute the maximum on the tail of the list, which is Y. Then we compare it with the head of the list, and we return, as a result, the greatest between these two elements. So it seems right. If you have to write down a program, you write something like this, I think, at least in a declarative programming language. And so we expect that the interpretation of this definition is what we expect to be, so that the result is actually the maximum of the list. However, as we will see in the standard theory, this is not. So let's start by the inductive interpretation of the definition. So this is the most standard interpretation of the definition. When you write down the recursive program in any programming language, you are actually reasoning inductively. And in this setting, the inductive interpretation is defined as the set of judgment having a finite proof tree. So we are required to use a finite proof. So to start from some axioms and apply them rules to derive something. So what happens in the examples? On finite list, everything works well. This is good. But on infinite list, the predicate is undefined. So why it is undefined? So this means that we cannot derive any judgment. And this is quite intuitive, since to compute the maximum of a list, we need to inspect all the elements of the list. But if the list is infinite, we cannot do this in a finite number of steps. So it is quite obvious that we cannot do this with a finite proof tree. And so in the literature, there is the coinductive interpretation, which is the dual one, and actually remove this limitation. So the coinductive interpretation is the set of judgment that has a finite or infinite proof tree. So we have no restriction on the kind of tree we are using. And here, everything still works well on finite lists, since we still can use finite proofs, and so everything is the same as before. But on infinite lists, now the predicate is undetermined, so we can prove too many judgments. This seems strange, but let's consider an example. So we have the infinite periodic list, 1, 2, 1, 2, and so on. And we expect that the only judgment we can derive is that the maximum is 2, since there is no other element. And this can be done by that proof 3, which is an infinite proof, in which we apply infinitely many times the second rule. And we can derive that the maximum is 2. But we can also build in the same way that other proof and derive that the maximum is 5. And this is quite strange, since 5 does not belong to the list, and so it cannot be the maximum of the list. So what happens is that the inductive interpretation is too small, so we have too few judgments, and actually it is the smallest possible interpretation, and the coinductive interpretation is too large, and it is the largest possible interpretation. But in this case, we need something which is in the middle between these two sets. And the standard theory does not allow us to choose such a set. So last year we extend the framework, proposing this notion of coaxioms, and essentially the definition is this one. So we have a standard inference system, which is the first component, and the second component is a set of judgments called coaxioms. They are very similar to axioms, as the name reminds, but they are used in a very special way, since they are used to control the semantics of the interpretation. So the definition of the maximum predicate, we have the same inference system, and then we add that coaxiom that says that the maximum of a list is the head of the list. Essentially, this, as we will see, add the constraints that what we compute as maximum is actually an element of the list. So, formally, the interpretation generated by coaxiom is constructed in 2 steps. So first, we add the judgment, add the coaxiom to the inference system as axioms. So we add to the inference system a rule with no premises, and where the conclusion is an element of gamma, and we take the inductive interpretation of this inference system. Then, as a second step, we forget about coaxioms, and we take the coinductive interpretation of the standard inference system, but restricted to the set we have computed at the previous step. Here, restricted means that we are only allowed to use rules where the consequence is in the set computed at step 1. Okay. Essentially, this says that we reason coinductively, but we restrict the universe in which we can work. So we can use less judgment in our derivations. So using a proof theoretic in the proof theoretic fashion, the interpretation generated by coaxiom is defined in this way. So the set of judgment where we have an arbitrary proof 3, so we are reasoning coinductively, but we require that each node of the tree has a finite proof in the extended system. So as a finite proof where we can use as initial assumption also coaxioms. And in this way, it is clear that we filter out the coinductive interpretation in some way, since we take also infinite proofs, but not all infinite proofs, only that one that satisfies the second additional constraint. And so we get a set which is smaller than the coinductive interpretation. So what happens in the example? The example, so we take the first derivation, the correct one. We can build that finite proof starting from the coaxiom, and so this derivation is valid. So we can still derive that the maximum of the list is 2, but considering the other derivation, which we want that is not correct, what happens is that we cannot derive any we cannot derive that the maximum is 5 with any finite proof, since, as I said before, the coaxiom compels us to start from an element of the list, and so what we can derive is always an element of the list, and 5 is not an element of the list, and so this derivation is not admissible. Okay, so what we have, we say that these semantics, this definition are more flexible, since changing the set of coaxioms is equivalent to changing the semantics. So we can interpret a definition in a more flexible way, since we can essentially choose the semantics by changing the set of coaxioms. And so we have only to explain, only to explain the word extension. Why we can say that this is an extension of the standard theory, since we have this very good property. Induction and coinduction are a particular case. So if we take as a set of coaxiom the empty set, we get an inductive interpretation, since intuitively having no coaxioms, we cannot use any infinite proof, and so we are inductive. And if instead we take as a set of coaxiom the universe, so all the judgment, all infinite proofs will be admissible, and so we are going coinductively. And so the standard theory is a particular case of this framework. Okay, that's it. This is the theoretical part. So let's consider an application. We want to model. So the application probably is not even an application, but we want to model the semantics of the programming language, and in particular model the non-terminating program. So when we have a Turing complete language, we know that there are programs that does not terminate, and some programs we want that we want not to terminate, since, for instance, the server should continue computing forever, hopefully. And so we want a way to formally define this semantics, to reason about this, to prove properties such as type soundness, equivalence, correctness, and whatever you want. So as an example, we take the lambda calculus, which is, I think, the most simple programming language that we can consider. In the lambda calculus, this is the syntax. In the lambda calculus, everything is a function, and values are functions, and lambda abstraction, that is lambda x dot e, should be thought of as a function that take a formal parameter x, and where the body of the definition is the expression e. And then, as expression, we can either write a function, so a value, a variable, or a function application, so the expression e1 applied to the expression e2. And so there's nothing more, so only 3 constructs, but as a note, as a side note, this is, I think this is the most powerful programming language we can use, since it is Turing complete, so any computable function can be written in this programming language, and so I think it is enough to reason about programming languages. So we have to model the semantics of this, so how we can evaluate an expression. We have convergent programs, so programs that terminates in a finite number of steps, and the semantics of this is modeled by that judgment that says that an expression E terminates and returns as a result a value V, and this can be defined by that 2 rules. So the first rule says that a value evaluates to itself, there's nothing to do, and to evaluate an application, we have first to evaluate the first argument, so E1, and get a function, lambda x dot d. Then we evaluate the second argument, E2, and get another value. And then we perform the application of the function. And the application is performed by substitution. So we take the body of the function and replace all occurrences of the variable x with the value v, evaluate the resulting expression, and get the final result. Okay. This is a way of performing an application. It's actually a function application, nothing more. And since we want to model convergent computation, so program that terminates, we take the inductive interpretation of this system. Since we want to get the result in a finite number of steps, and so we must use finite proof trees. But we have also divergent computations modeled by that judgment that says that E diverges, essentially, does not terminate. And the rules are that three rules, which are quite intuitive if you think a moment about this. So for values and variables, there is no rules since they cannot diverge. A value is a value, you cannot evaluate anymore, and a variable is the same, are normal forms in hardcode in the theory. But so the only expression that can diverge is the function application, and can diverge for three reasons mainly. So we evaluate the first argument and it diverges, and so also the whole application diverges. We evaluate the first and we get a result, so it terminates, and so we start to evaluate the second argument, and then the program diverges, and so the whole program diverges. And then we can evaluate both the argument and get something in a finite number of steps, and then evaluate the function application, and this premise diverges, and so the whole expression diverges. So this rule should be interpreted coinductively, since there is no axioms, so if we use the inductive interpretation, we get the empty set as the semantics. But more intuitively, we want to model something that does not terminate, and so that continues computing for an infinite number of steps, and so we need an infinite proof to derive this. And so we should take the coinductive interpretation of this system. So what we have an inductive inference system for the convergent semantics, and we have a coinductive inference system for the divergent semantics, but we want a single semantics. So we want a single definition for the semantics of the lambda calculus. And so we should put all the roots together. Roots are exactly the same. I have only merged the two rules for the application in a single one, since it is the same. It simply says that the function application could either converge to a value or diverge. V with the subscript infinite means only this. And now we have to choose an interpretation for this definition. Which one? This is the problem, since if we take the inductive interpretation, we cannot derive anything for divergent programs, since we can use only finite proof trees, and so we cannot derive anything for infinite computations. If we take the coinductive interpretation, we get a very strange semantics, since we can also derive that some divergent program converges. We mix together values, and divergence is a very mess. So the coinductive interpretation is not good. And so we need something which is in the middle, again. And so we have that coaxiom that essentially says that coinduction is only applicable to prove divergence. So we can use infinite proofs only to derive that the program diverges, and that's it. So this is it can be proved that this is semantics is correct. We have done this in a paper published at Uppsala last year. We can use this to prove type soundness and other properties. So this is a unique definition that models both convergent and divergence computation. So concluding what we are currently doing with this stuff. So we are working on richer semantics. So rather than simply modeling that the program diverges, we want to have some more information. So add to the semantics also a representation of the behavior of the program during its infinite computation. So for instance, input-output behavior, memory usage, or a computation of the cost of the execution of the program, and whatever you want, essentially. And the application to this setting, so to model infinite behaviors, requires a smooth extension again of the framework. So we have to add also co-rules in addition to coaxiom. Essentially, we allow coaxiom to have premises, and the semantics and interpretation is exactly the same. So there is no additional theory you have to develop in general. And that's it. Thanks.
So, any questions for Francesco?
very stupid question, but it's like a relaxation of the Arctic problem. So you have the inductive and the coinductive system, and I try to find something in between because I want to deal with problems that are complex, like the halving.
Actually, no, it doesn't. It's not related to the halving problem, so we do not care about the computability of this definition. We simply want to model that the program's diverges. Okay. I'm not asking if the program. We don't want to solve the problem that given a program, we want to say that this diverges or not. We simply want to model the semantics of the program.
I would like to know if there exists some rationale behind the way the coaxium are chosen. So, why is the way you reach the idea that the coaxium for the maximum was that one, which is quite not the natural? Something is false, is neither true, neither false.
Okay, so
and in general, maybe if you have any inductive definition with this kind of so your technique can be applied in any case, or there are limits. So there are cases where you cannot find the good coaxium. So I give you an inductive.
I got it. So when I said that we are working on semantics for infinite behavior, we are taking a very abstract approach. So we want to give a canonical way to, starting from semantics for convergent computation, we want to have a canonical way to extend this semantics to get a semantics that include also divergent computation. And this process includes the choice for coaxioms, for rules in that case. And so we are currently trying to find out a way to give canonical patterns for that particular situation for rules. And this can be done since we have better understood which is the algebraic structure beside the coaxioms. So in that setting we can give a canonical pattern for choosing coaxioms. In the other cases, it depends on who is using on what you want to define. So the intuition I have is that coaxioms can be used to with coaxiom you define when you want to use coinduction. So you define the cases in which you allow the definition to go to use infinite rules. And so in some sense this is the intuition. I don't know how. There are other ways. So there are other proof-theoretic characterizations which we can think as coaxiom as something that goes to the infinite in some sense, but there is still no way to give, in general, to give a canonical choice of coaxioms. And for the second question, there are cases in which this technique does not work. Obviously, yes, since it is not a silver bullet. And so there are kinds of predicates for which we cannot choose, for which we cannot. There is no coaxiom that gives a complete definition, so we can get something that is sound with respect to the expected semantics, such as the inductive interpretation is always sound since it is a smaller step, but we cannot get the full definition in some sense. I don't know how to.
I have another one. So usually one thing you exploit when you have either inductive or coinductive definition is that you have some well-known principle. So inductive is the smallest something. So if you want to prove that your thing is included in something else, you have a principle. Same way with the coinductive interpretation. Do you also have something similar here? Like if I define something using your system, then I have an associated proof principle? Or?
Yes, so we have a generalization of the coinduction principle. I think I have a slide. This one. bounded conduction, is correct?
Yeah, it is.
Okay, it's the bounded conduction principle, and so, like the conduction principle, this can be used to prove completeness of a definition. So we have a set which is a specification, and we want to prove that this, that our definition, that this set is included in our definition. And to do this, we have to do two things. So we have to prove that the specification is a postfix point of that function, which is the one-step inference operator. So it is something like the coinduction principle. We have to do a proof of consistency. And then we have to prove that this set is bounded. So all the judgment in the specification can be derived by finite proof in the extended system. In a sense, this step says that all the judgment in the specification are admissible to build proofs, infinite proofs. And the postfix point, the second condition, the consistency condition, says that we can actually build infinite proofs. And so, proving these two facts, we get the completeness as the coinduction. Coinduction simply removes the boundedness requirements, and we have the standard coinduction. So this is the proof principle. We have also some principle to prove soundness of definitions based on what is less standard and less beautiful. It's much more ugly, so I don't show you this.
Okay, there are no other questions, then thank you again.